Welcome to this lecture on animal behavior. Today, we are diving into one of the most dramatic and fascinating forces in nature, intra-sexual selection. If you have ever wondered why certain animals develop massive weapons, engage in brutal fights, or grow to enormous sizes, you are in the right place. We're going to build our understanding of this concept from the ground up, looking at both the biology and the mathematics behind the battle for reproduction. Let us start with a simple analogy to build our intuition. Imagine you are at a bakery, and there's only one single slice of the most delicious chocolate cake left. However, there are 10 incredibly hungry people who desperately want it. What happens next? Naturally, those people might start arguing, pushing, or trying to outsmart each other just to get to the front of the line. In the animal kingdom, this cake represents the opportunity to mate and pass on genes. The hungry people in this scenario are usually the males of a species, fighting for that single valuable opportunity. Building on our bakery analogy, we must ask why this intense competition exists in the first place. The answer lies in biological investment. Because females invest a massive amount of time and energy into producing energy-rich eggs and raising their young, they become a rare and highly valuable resource in the mating pool. They simply cannot reproduce as quickly or as often as males can. Therefore, males find themselves in a position where they must fiercely compete with one another just to get the chance to mate. This fundamental imbalance in reproductive rates sets the stage for intense rivalry. Now that we understand the biological reality, let us formally define what we are looking at. Intra-sexual selection is a specific mechanism of sexual selection where members of one sex, typically males, compete directly with each other for access to the limiting sex. The prefix intra literally means within, so this is strictly a within-sex rivalry. It is very important to keep this completely distinct from intersexual selection, which is the process of females actively choosing a mate. Here, we are focusing entirely on the battles, both physical and psychological, that happen between males before any mating even occurs. Understanding this definition helps us see its incredible impact on animal bodies and behaviors. This relentless evolutionary pressure heavily favors any physical or behavioral traits that enhance an individual's ability to fight, intimidate rivals, or secure prime territory. Over thousands of generations, this competition leads to the development of extreme physical traits. Think of the massive antlers of a moose, the heavy armor of a rhinoceros beetle, or the sheer massive body size of an elephant seal. It also drives behavioral adaptations, such as aggressive posturing, loud vocalizations to establish dominance, and even sneaky mating tactics employed by smaller males. So, why is studying these extreme traits so important for scientists today? Understanding intrasexual selection is absolutely crucial because it explains sexual dimorphism, the widespread phenomenon where males and females of the same species look completely different. Without this concept, biologists would be baffled as to why a male deer grows massive antlers that require immense energy, only to shed them months later. Furthermore, in the real world, wildlife conservationists use this exact knowledge to manage endangered populations effectively. They must ensure the sex ratio and habitat structure allow for natural competition without causing excessive mortality among the males. To truly grasp how conservationists manage these populations, we need to measure this competition mathematically. This brings us to the operational sex ratio, or OSR. Conceptually, this formula tells us the ratio of active competitors to available mates at any given specific time. In the equation, OSR stands for the operational sex ratio. The numerator, MR, represents the number of sexually receptive males that are ready to mate. The denominator, FR, represents the number of sexually receptive females available at that exact same time. When the number of receptive males increases while females stay the same, the OSR becomes highly skewed, meaning competition becomes incredibly fierce. Conversely, if receptive females increase, the ratio drops and male rivalry decreases significantly. Now that we have our formula, let us see this with a concrete example involving a local pond of bullfrogs. We are given a total population of 150 adult males and 150 adult females. However, because females take time to produce eggs, only 10 females are sexually receptive tonight, while all 150 males are ready. We are asked to calculate the operational sex ratio. We choose this formula because we must ignore the total population and focus only on the active mating pool. We substitute 150 for the receptive males in the numerator and 10 for the receptive females in the denominator. Dividing these gives us a final answer of 15. Physically, this means for every single receptive female, there are 15 males actively competing, indicating extremely intense and exhausting physical rivalry tonight. This intense rivalry we just calculated can be visualized to show its evolutionary impact. Here we are looking at a graph that plots the operational sex ratio on the horizontal axis, ranging from a 1-to-1 ratio up to a highly skewed 10-to-1 ratio. The vertical axis represents the intensity of intra-sexual selection, which includes aggression levels and the size of physical weaponry. Notice the thick black curve sweeping upwards? It shows an exponential relationship. As the ratio of males to females increases, the competition becomes fiercer. Following the curve, you can see illustrations of deer antlers growing progressively larger and more complex. This diagram beautifully teaches us that a highly skewed mating pool directly drives the rapid evolution of massive, costly weapons in the animal kingdom. This visual relationship between competition and weaponry leads us to our next mathematical tool. How do we quantify the actual evolutionary pressure pushing these traits? We use the opportunity for sexual selection formula. Conceptually, this tells biologists the maximum possible evolutionary pressure acting on a population. In this equation, IS represents the opportunity for sexual selection. The numerator, VM, stands for the variance in mating success among males, which means how unevenly the matings are distributed. The denominator, W, represents the mean or average mating success of the entire male population, and we square it to normalize the value. Physically, if VM increases because a few dominant males monopolize all the females, IS skyrockets. This high value means rapid evolution of weapons and body size. Now that we have defined this evolutionary pressure, let us calculate it for a real population of elephant seals. We are given a remote beach with 20 male elephant seals. The average mating success, W, is exactly 1 mating per male. However, because one massive beachmaster secures almost all matings, the variance, V sub m, is given as 17.1. We are asked to calculate the opportunity for sexual selection. We use this specific formula because it reveals the true intensity of evolutionary pressure based on mating inequality. We substitute 17.1 for the variance in the numerator and 1 squared for the mean in the denominator. This gives us a final answer of 17.1.
Physically, this exceptionally high number explains why male elephant seals have evolved to be 4 times larger than females, as evolution heavily rewards any trait that helps a male win.
We have covered a lot of ground today, so let us reinforce the most important ideas from this topic. First, intrasexual selection is a powerful evolutionary engine, driven entirely by same-sex rivalry, usually among males competing for females. Second, this intense competition is the primary biological reason we see spectacular weapons, massive body sizes, and fierce territorial aggression. Third, by using mathematical metrics like the operational sex ratio and mating variance, we can accurately predict just how intense this competition will be. You have now seen both the biology and the math behind this phenomenon. Ultimately, this teaches us a profound lesson. In nature, mere survival is not enough. An animal must also outcompete its rivals to successfully pass its legacy to the next generation.